A city existed where the lights never fully turned off, but something stranger was happening. One morning, Stickman opened the map of Line City and froze. The roads hadn't disappeared, but something far more disturbing had changed. Between certain locations, the roads simply didn't exist anymore. And between others, there was a road, but only one traversal was allowed before it vanished forever, as if the city itself was forgetting how it was connected. Stickman whispered, "This isn't a map, it's a puzzle." But he didn't know yet. This puzzle wasn't just of the city, it was of mathematics itself. And then the first clue appeared. Every intersection had a number written beside it. 1, 3, 2, 5. Some points had many roads coming out of them, others had only one. Stickman noticed something unsettling. If he tried to start anywhere and cross each road exactly once, covering the entire city seemed impossible. But why? And this is where the first secret of graph theory begins. The city wasn't really a city. It was a graph. The points were nodes, and the roads were edges. Stickman slowly drew circles over intersections and lines between them. "If I want to solve this," he said, "I need to understand what pattern these connections are hiding." Then he found an old archived file. Königsberg Bridge Problem. A city with 7 bridges, where people tried for centuries to find a path crossing each bridge exactly once. Stickman stopped. So this problem has existed for hundreds of years. But then the situation took a darker turn. Line City had the same structure hidden inside it. Some nodes had an odd number of connections. And in graph theory, that detail changes everything. If more than 2 nodes have an odd degree, then a single continuous path that uses every edge exactly once becomes impossible. Stickman marked the nodes, one odd, another odd, then another. Each new discovery made the system more broken, or more intentional. "This city isn't random," he said. "It's designed this way." But by whom, and for what purpose? At the center of the map, another symbol started to glow. A single arrow pointing toward an unknown region. Stickman followed it, and arrived at a locked gate. Engraved on it was a sentence. "Only those who understand every connection may enter." Now the problem had changed. This wasn't just about roads, it was about traversal. Stickman muttered, "If I want to travel every edge exactly once, I need an Euler path." The moment he said it, the map flickered, as if it recognized the term. The rule of an Euler path was simple, yet powerful. A graph contains a path that visits every edge exactly once, only if it has 0 or exactly 2 nodes with odd degree. Stickman looked again at the map. His expression tightened. So this entire system is testing whether such a path exists. But another layer emerged. Next to the gate was a digital panel. It displayed minimum cost route required, and beneath it, multiple possible paths appeared. Some were short but dangerous, others were long but stable. Stickman hesitated. This is no longer an Euler problem. This is optimization. Now graph theory revealed its second face, weighted graphs. Edges were no longer just connections. They carried costs, distances, risks, time. Stickman assigned values to every road, 1, 4, 2, 7, and tried to find the best route. But something strange happened. Whenever he picked the locally best option, the overall route sometimes became worse. So greedy choice doesn't always work. That realization hit harder than expected, because it revealed something deeper. Graphs are not just maps, they are decision systems. Every edge is a choice, every node is a state, and the entire structure becomes a decision space. But the real twist was still ahead. Suddenly, the map reset. All edges reappeared. But the structure had changed. Some nodes became isolated, some formed tight clusters, others formed loops that could trap movement endlessly. Stickman stepped back. This isn't just routing anymore, this is connectivity. Graph theory revealed its third principle: connected components. If a graph is not fully connected, then no path can traverse everything. Stickman began separating the map mentally. Which parts are reachable? Which parts are isolated? Which parts are traps? Each analysis revealed deeper structure. The city wasn't hiding paths, it was hiding its own architecture. And then the final clue appeared: a node that didn't exist on the map, yet somehow it influenced every connection. Stickman stared at it. This node is invisible. But it was real, because every edge decision seemed to depend on it. Then realization hit. The invisible node wasn't physical. It was a rule, an algorithm. The hidden logic that defines how connections form. Graph theory wasn't about drawings. It was about relationships encoded mathematically. Social networks, internet routing, GPS systems, even neurons in the brain. All of them are graphs. Stickman placed his pencil down. The gate slowly opened. Inside, there was no treasure, only a mirror. And on the mirror, a message appeared. You didn't solve the city. You understood the structure. Stickman finally understood. Euler Paths, shortest paths, connectivity. They weren't separate ideas. They were different perspectives of the same question. How are things connected? If you understand connections, complexity becomes manageable. If you ignore them, even simple systems become impossible. The map slowly dissolved, but one final message remained. Next time you see a system, don't look at the objects, look at the connections. Stickman turned toward the viewer, as if the investigation was no longer just his. Graph theory isn't just mathematics, he said. It is a lens to see the world. And if you think this was just a city puzzle, then the next investigation goes deeper, because every network hides another network underneath it, waiting to be discovered.